Hello, welcome to our Semiconductor education program. This is Vincent Chang. In this lecture, we are going to continue what we learned from the previous lecture, which is the crystal oscillator, and try to explain the frequency response and how to solve a crystal oscillator. Crystal oscillator part 2, frequency response, explained. So let's try to get the so-called crystal reactance first. But before we get the reactance, we need to review what we have learned from the previous lecture. So the first one, equivalent circuit. This represent the equivalent circuit, approximate equivalent circuit of a crystal. And then you solve this equivalent circuit, you can get the crystal impedance. And inside the expression, with this expression, is actually there are two important parameters embedded inside this crystal impedance. The first one in the denominator, which is called the series resonant frequency. It's more the intrinsic resonant frequency directly related to an interesting phenomenon from a crystal called electromechanical resonance. But the second one from the denominator of the crystal impedance is called parallel resonant frequency. Okay, and you can also interpret this parallel resonant frequency by grabbing the two terminals of the L and try to look at the equivalent capacitance from the circuit. Then you are going to get the series combination of the two capacitors. This explains this equation, the parallel resonant frequency. So now look at the title, crystal reactance. Crystal reactance. To get the reactance, because this circuit shows it's the purely reactive. There's no resistance. There's no real part. There's no real number. So if you replace the complex frequency S by J omega, then you're going to get what? Get negative J omega in the denominator. And then negative omega square in the numerator and negative omega square in the denominator. So let's multiply both numerator and the denominator by -1. Then you are going to get this. Okay? So it's the purely imaginary number. So it's the J. So then the imaginary part is called the reactance. So Jx. So Z is the impedance. Jx is called reactance. Okay? So the capital X as function of frequency equals -1 over omega Cp and the big parenthesis like this. So this is the crystal reactance. So our next task is to try to find out its frequency dependence. In other words, when you increase the frequency from the low frequency to a very high frequency, how the crystal reactance is going to behave. So we're going to investigate without doing this, we cannot solve a crystal oscillator. So frequency response. The vertical axis represents the crystal reactance. The horizontal represents the frequency. So let's try to scan from the zero frequency, the DC, to the very high frequency. See how the crystal reactance behaves. But before we do this, we need to take a closer look for these two frequencies first. Okay, what two frequency? A series resonant, omega S, and omega P. First of all, look at the denominator. Okay, the same inductance, but different capacitance. But which one is smaller? The second one, the parallel one, is smaller, right? So if the the denominator of the parallel one is smaller. So after inverse, it's bigger, it's higher. So parallel is on the right-hand side of the series. So parallel is higher than the series resonant frequency. So omega p is higher than omega s. And then remember, I told you in the previous lecture, the CP is much, much higher than CS. The parallel capacitance is much higher than CS. What does that mean? So you see on the frequency axis, let's mark omega p is on the right-hand side of the omega s. Omega p is higher than omega s. And now I'm talking about CP, the order of magnitude. Another same. CP is much higher than the CS. What does that mean? Look at the denominator of omega p. So when CP plus CS, CS is negligible. So CP got canceled out. Then you go back to the omega s. So these two frequencies are actually very close. The omega p is actually very, very close to omega s. In other words, this frequency band, the band between omega s and omega p is wide or narrow. It's very, very narrow. It's very, very narrow. So remember, this blue band is actually a very narrow band. A very narrow band. So these two frequencies are very, very close. Okay, this is very important to remember. So now, let's try to scan. This is actually a lesson from, you were supposed to learn this when you were a freshman college student, right? Calculus, okay? So when omega is the DC, omega is 0, so it's infinite. It's infinite. But why infinite? Positive or negative? Negative. Because parentheses represent a constant, a positive constant. So negative infinity. So it's infinite. And then when omega start increase, the denominator goes up. So after inverse, the value goes down. But the value goes down is the negative value with the negative sign. So it goes up like this. So until when omega equals omega s, then pay attention to the numerator. So numerator goes to what? 0. Goes to 0. Okay? And then penetrate passing omega s, and then because it's very, very narrow. And then once it reaches omega p, then what? Then denominator. Pay attention to the denominator. But the denominator, because the approach is from the left-hand side of the omega p. So when the denominator 0 is actually called negative 0. So with another negative sign, the two negatives got canceled out. And 0 in the denominator flipped. So make the whole expression goes to positive infinite like this. Right? And on the right-hand side, if you approach omega p from the right-hand side, from your right-hand side to the omega p, then the denominator of the highlight becomes a positive 0. So with the negative sign, with another negative sign, then the total x is going to go what? Go to negative infinity, like this. And then when omega increase, the total x is going to rising, like this. But when omega approach the infinite, the big parenthesis approaches what? Approaches 1. And then the left-hand side item next to the parenthesis approaches 0. You time these three together. Negative times 0 and times 1. So it's the negative 0. Okay? So it's below 0, but it's very close to 0, like this. You get it? So this is the frequency response of the crystal reactance. Now, above the 0, on top of this response, X is positive. On the bottom of this response, of this spectrum, the capital X is negative. So what do we mean by the negative X? It represents the crystal behaves like a capacitor. So with this two band, the green band, the crystal behaves as a capacitor. So this is capacitive. The crystal is capacitive. But within the band, the blue band, where X is positive, as X reactance is positive, means the crystal behaves as an inductor. Okay? So important, remember this. So from low frequencies to high frequency, the crystal's behavior from starting from the capacitive first and passing through a very narrow band where it is inductive and then go back to the capacitive. Capacitive, inductive, and then capacitive. So now, it's your time. So I'm asking you, let's bring this crystal oscillator back. This is the crystal oscillator. It's based on so-called LC-tuned oscillator. But we replaced one of the component with a crystal, with a quartz. Okay? So let's say if the quartz for the intrinsic resonant frequency, the series resonant frequency, let's assume the quartz frequency, the frequency of the quartz, or the intrinsic resonant frequency of the quartz, let's assume it's the 47 megahertz. Usually, this kind of spec is used to for the do the remote control, the car. Okay, 47 megahertz. So now, I'm asking you to solve this oscillator. What is the frequency of oscillation? So what is the frequency of oscillation of this oscillator? Okay, I'm asking you the oscillator. When the resonant frequency of the quartz, the intrinsic resonant frequency of the quartz is given. You can say the intrinsic resonant frequency. You can say it's the series resonant frequency. You can say it's the resonant frequency related to the electromechanical resonance of the quartz. So what is the frequency of oscillation for this oscillator? Okay. Before you solve this, take a screenshot of this. Before you solve this, let me remind you, because it's based on the LC-tuned oscillator. To make sure the Barkhausen criterion can be satisfied. So the Barkhausen criterion give us this first requirement. The sum of the three individual reactants has to be 0. The second requirement to start the LC-tuned oscillator, the gain of the inverting needs to meet this requirement. There's the minimum gain, the minimum gain. Okay, so now I give you, I think it's the 1 minute is enough. So it's 1 minute, try to solve the frequency of oscillation of that crystal oscillator. So let's pause. So what's the frequency of oscillation? Let's unveil this. The frequency response. Because as I mentioned, when we review the LC tune oscillator, to satisfy the Barkhausen phase criterion, the sum of the three individual reactances has to be 0. So now, within the frequency selective network, with that frequency selective network, the purple highlight, you have seen the C1 capacitive. X1 is less than 0. X2 is also less than 0. So which means the X3 has to behave as what? An inductor. The X3 has to be an inductive. So when X3 has to be inductive, what does that mean? This means the frequency of oscillation, to satisfy this, there is only one possibility. The frequency of oscillation has to be within the blue band, right? The frequency of oscillation has to be located within the blue band. In other words, the frequency of oscillation, the lower bound of the blue band is omega s. The upper bound is omega p. Has to be within this range. Larger than omega s and less than omega p. But remember, I said this two frequency is very, very what? The lower bound and the upper bound is almost overlap. So this curve is actually look like a delta function. So omega 0, the frequency of oscillation, if you treat this blue band's curve, the curve within the blue band as a delta function, there's only actually one frequency. So omega 0, the frequency of oscillation, is actually the intrinsic series frequency, the intrinsic resonant frequency of that oscillator. So which is defined as 1 over square root of L CS, series capacitance. So the highlight, the major takeaway from this lecture, we can take advantage of an approximate delta function behavior within the blue band, the inductive region. And we can analyze, we can design a crystal oscillator, which oscillation frequency is almost decided by the crystal's resonant frequency itself. Okay? The whole circuit's frequency of oscillation can be purely decided by the crystal's resonant frequency itself. So assuming if you can find a crystal with a very stable resonant frequency, when time changes, when temperature changes, the frequency of the resonant frequency has not changed. If you can find this kind of crystal, then you can create an oscillator with a very, very stable oscillation frequency. This is also the core concept for a crystal oscillator. So I hope you learned something, learned the core concept from the crystal oscillator from this lecture. Thanks for watching.